Very well. We are about to embark on the reactivity roads that pertains to all these molecules. And pretty much what we're going to be looking at exclusively is how you transform from one carbonyl compound to another within the same oxidation state. So you're not really reducing anything and you're not really oxidizing anything. You're at the same oxidation level throughout. Um, So what we're gonna do is just look at all the variations, right? How you take a carboxylic acid and turn it into an acyl chloride. How do you do that with the acid anhydrides? How do you turn a carboxylic acid into an ester, into an amide, into an nitrile, etc., etc.? So we'll see how this all works. Now, one thing that's important to point out right now is that in terms of reactivity, the acyl chloride's the most reactive out of the different derivatives. Second, by the anhydrides, that's followed by the esters, and then the amides are a lot less reactive, generally speaking, right? And then carboxylic acids, technically, you can go from most of them back and forth under the right conditions, but there are some pathways that might not be particularly helpful to you, and you'll see eventually which ones those are going to be. But we're going to go one by one through each of these pathways. So the first one is the conversion of a carboxylic acid to an acyl chloride. And what this is all about is simply treatment of the carboxylic acid with thionyl chloride, shown right here on the right side of this reaction. So now basically what happens is that your carboxylic acid attacks your sulfur from the thionyl chloride. That opens up that bond, turns into a single bond. And the newly formed adduct, because of the presence of really good leaving groups, aka the chlorides, the reformation of that sulfur oxygen double bond takes place, kicking away one of the chlorides in the process. So when this happens, now that you have freed out one of the chlorides, you could think of this entire fragment here on the right side of the molecule as being nothing more than a really good leaving group. So a deprotonation with your chlorides and a proton shuffle such that you end up protonating the carbonyl here on the left side of the equation allows you to basically turn this carbonyl carbon into a really excellent electrophilic site, right? You have technically a good leaving group here on the right side, and then you got this oxonium cation to really emphasize the idea that yes, this carbon is waiting for nucleophiles to attack. So the chlorides wastes no time to abide by that request, right? So it attacks with 2 electrons, it pushes the pi bond back exclusively onto that oxygen, thus rendering that oxygen neutral. But now you have a tetrahedral site right here, right? And what happens right now is that we eliminate a leaving group. And this time around, the leaving group we're going to eliminate is the thionyl group right there because of 2 reasons. So this comes back down and it kicks off the group. This turns into sulfur dioxide, and then you have chloride also being produced in the process. Now, the sulfur dioxide is actually a gas the moment it's formed. So once you form it, as long as the flask is open to the atmosphere, it's gone. It's basically lost. And that drives the reaction forward to completion. And of course, as you can already surmise, the last chloride that's left in there is simply serving the purpose of removing a proton from that carbonyl to give you your acyl chloride. So typically you do this with the presence of a tertiary amine to remove the HCl, but for my purposes, this is more than enough as far as showing how the formation of the acyl chloride takes place. Now, the acyl chloride, as we'll see momentarily, can be used to prepare any of the other carboxylic acid derivatives. So it's a very powerful and useful starting point to make functional group transformations. But before we get to that point, I want to show you what else you can do with the carboxylic acid. So if you basically treat a carboxylic acid with a strong base like sodium hydroxide, um, you will deprotonate the carboxylic acid and you will generate a metal carboxylate, in this case sodium carboxylate. And although this is not an amazing nucleophile, it's relatively okay for certain things. And specifically, if you mix your sodium carboxylate with an acyl chloride, like the one right here, right? So we have butanoyl chloride reacting with sodium acetate. Well, the acetate can act as a perfect nucleophile to butanoyl chloride. You attack the carbonyl, you break that double bond to form a tetrahedral intermediate, and then the double bond is reformed, kicking away the good chloride leaving group, right? And once that happens, once the double bond gets reformed and the chloride takes off, the chloride incorporates itself with sodium to basically form and precipitate sodium chloride in your mixture. At the same time, you have now prepared um, an asymmetrical acid anhydride. So this is one of the simplest ways to go about making anhydrides, in my opinion. Okay, now following along that route, let's see what carboxylic acids can do as far as making esters. All right, so the best way to do this is to perform a reaction under acidic conditions specifically. If you don't, it can be futile to try to make that ester, but let's show you what happens here, right? So under acidic conditions, like in this case sulfuric acid, you will protonate your carbonyl carbon in the carboxylic acid. And once this happens, your carbonyl carbon is now activated for nucleophilic attack. So usually when this takes place, you do it in the presence of alcohol. Ideally, the alcohol is the solvent, right? So you're doing this with alcohol solvent, as well as your carboxylic acid being there, right? And you only add a little bit of sulfuric acid. It's technically a catalyst for the process. But the alcohol sees the activated carbonyl and it attacks that carbon, right? Ultimately, what happens is that you break that pi bond initially, make the tetrahedral intermediate here. And the second thing, of course, is that the oxygen, of the alcohol comes along with its carbon chain as well as its hydrogen. So that carbon chain and the hydrogen has to be there initially. And because that oxygen now has 3 bonds, that's where the positive side sign resides. Okay, so the last portion right here is that you have to basically shuffle these protons. So you're going to deprotonate it, and the hydrogen sulfate is more than enough to serve this purpose, right? You can come, remove that proton, bring it back to the oxygen, making it neutral. But then that sulfuric acid that we've just reformed comes back around and dumps the proton, if you will, on a different oxygen, one of the hydroxyl oxygens specifically. So if we carry out this reaction, right, and we do the protonation, what you're going to end up doing is creating a water leaving group in this molecule. And kind of reminiscent of the hemiacetal-acetal reactions we talked about with aldehydes and ketones, the hydroxyl that's present on that same carbon comes back down, brings its 2 electrons to create a double bond, and in the process kicks away that water, yielding a protonated ester. So the last event right here is that we need to remove that proton to get it into a neutral ester altogether. So once again, your hydrogen sulfate comes around, removes that proton, yields the neutral ester, and of course reforms the sulfuric acid catalyst in the process. So this is a pretty efficient way of making esters. All right, now amides. It's a little bit of a different story. And one way to make amides from carboxylic acids, which is not it's not the greatest of reactions. It kind of works to an extent, but it is very finicky. First of all, you have to remember that when you are dealing with amines and you have to perform the reaction under acidic conditions, the amine is a basic substance. And if you make the solution too acidic, ultimately what's going to happen is that all your nucleophile is going to be fully protonated and it will no longer work as a nucleophile. So there's a sweet spot that you have to hit for this reaction to work well. Generally, it is said that if you hit a pH of about 4, that's acidic enough that it can catalyze the reaction, but not acidic enough that it will protonate all of your amine base present in solution. So what ends up happening is that you, in that case, protonate the carbonyl, kick those electrons back to your nitrogen. And granted, this is an equilibrium that is not now like super favoring the product side. If anything, is favoring this reactant side, but there is an equilibrium to it. So you have that protonation, right? And then the amine ends up attacking the carbonyl carbon, kicking away the electrons back to oxygen. Now, this time around, the nitrogen has 4 bonds, so now that's where the positive side resides. So what ends up happening right here is that we have to reshuffle the proton, right? We remove it with solvent, or we remove it with another equivalent of amine, right? So attack the proton, the electrons go back to the nitrogen. You end up with this intermediate, and then the ammonium that you've produced comes around and dumps its proton on one of the hydroxyls, right? So the hydroxyl attacks that proton, the electrons go back to this nitrogen to give you the amine again. And now you've created a water leaving group in your molecule. So the hydroxyl on the opposite end donates its electrons to create a double bond, and in the process kicks away the water. So you have this intermediate, this protonated amine intermediate, which at the end of the process gets deprotonated by another equivalent of amine, and the electrons go back to the oxygen. So this is how this reaction happens. But as I just mentioned to you, it's very finicky. The pH you have to hit just right, and even then, you're kind of fighting against equilibrium a little bit within the the first few steps. So it's not the most efficient way to making amides. As you'll see throughout the rest of the videos, there are other ways to get to it, and I would recommend that you make use of the other options as opposed to this one, because this one is not the greatest. Okay, so yes, very difficult. Okay, so with that, we're going to stop the video right here. That's basically the reactivity for carboxylic acids going to other things. But now we're going to look at what we can do with acyl chlorides, and you'll see that some of the issues that we were having with carboxylic acids can actually be circumvented with acyl chlorides. So we'll talk about that in the next video. I'll catch you then. Bye-bye.